At the heart of our galaxy hides a monster, a black hole called Sagittarius A. It's silent, invisible, yet powerful enough to shape the Milky Way itself. Tonight we'll uncover its secrets and the strange forces that surround it. If you enjoy exploring the unknown, please like, subscribe, and share, and tell us in the comments. Do you think black holes create or destroy more than we imagine? Thank you for watching. Now let's begin. The Milky Way appears as a soft river of pale light. But its centre is not soft and not pale. It is a crowded furnace hidden behind curtains of dust and gas that choke visible light and scatter it into silence. And within that silence the galaxy holds its tightest knot of stars, clouds, magnetic threads and drifting debris. From far out in the spiral arms the body of the galaxy looks calm, yet the central bulge carries a heavier glow, a swelling of starlight squeezed together by gravity, and within this glow lies a region so congested that normal sight fails. Here the dust lanes rise like dark mountain ranges against the starfield, and the only paths inward are through windows of longer wavelengths, the kind that slip past grains of carbon and silicate and announce that the heart of the galaxy is not empty but alive. The journey inward begins across a span of roughly 26,000 light-years from the Sun's neighbourhood, and as the view tightens, the stars grow numerous, and the space between them narrows until the concept of isolation loses meaning. Every direction holds a neighbour. Every neighbour casts a tide. The radiation climbs, the temperatures rise, and the interstellar medium turns from thin mist into a complex weather of shock fronts, shear and compression. Around the core, clusters of ancient stars orbit within a broad, rounded bulge, their motion stirred by the collective gravity of billions of suns, and by something deeper and more concentrated that draws on a scale beyond the ordinary sum of mass. Observatories carve a corridor through the dark. The Very Large Telescope measures motions of stars in the near-infrared, reading the heat that dust cannot swallow. The Atacama Large Millimeter or Submillimeter Array listens to the cool breath of molecules tracing their spirals and collisions in the gas streams that circle the centre. The Chandra X-ray Observatory watches high-energy light spark where matter slams into matter, while the Hubble Space Telescope, limited by dust, still adds scattered shards of structure in rare thin windows. Together they map an environment that does not sit still. Stars move at thousands of kilometers per second, yet in this central zone speed does not mean freedom. Speed means survival. Gas drifts inward as filaments and clumps that stretch and shear, twisting into rings and arcs around the unseen anchor. Magnetic fields thread the region like taut fibers, some running almost straight for dozens of light-years, others curling into loops that guide or resist the flow of charged particles. The circumnuclear ring, a torus of gas and dust a few light-years wide, feeds the inner region, the way an upstream estuary feeds a hungry inlet, and inside that ring the pace quickens. Gravity steadies the patterns, but not with peace. It steadies them in the way a storm settles into its own shape. The central parsec, a space spanning only a few light-years, carries densities and energies far beyond what the spiral arms know. Massive stars blaze blue and short, lived born in crowded nurseries and pushed around by shock waves from their elder siblings. Their winds, fast streams of particles collide and compress, making knotty shells of gas that drift and shatter. Supernova remnants mark the deaths of the heaviest of these stars, stirring the medium again and again, sending ripples toward the middle like tremors felt through bedrock. Though the crowd is thick, the pattern remains strangely ordered. Radio maps show filaments that stand almost upright like steel reeds, whispering of a coherent magnetic structure in a place that should be random, and this order feeds the suspicion that the heart does not only devour, but also organizes. Light here is not only a messenger, it is a survival story. Visible light vanishes into dust, but infrared light slips through radio waves, roll past the grains, and X-rays leap from hotspots where matter crashes into shocks. Each band reveals a different layer: cold gas in the millimeter, warm dust in the infrared, lethal heat in the X-rays, and each layer tells that the center breathes. It inhales when clouds drift inward and stall it, exhales when outflows or winds push back. However, the rhythm is not regular. Decades of monitoring by teams across continents show that sudden brightening episodes flicker from the compact core short bursts that hint at feeding events like small meals falling inward through turbulent streams. The Event Horizon Telescope aims for the final veil joining radio dishes across Earth into a single instrument wide as the planet capable of tracing light, bent by gravity near the ultimate descent. Its image of a thick ring wrapped around a darker interior does not show a literal surface, but the ghost of space-time bending around a place where light itself loses the argument with gravity. Within this ring there is no solid edge to strike, only a horizon of no return, where paths curve inward and never reappear. Yet the path to this horizon is not a straight fall. It is a gauntlet of physics where friction heats, gas magnetic turbulence churns the flow, and angular momentum fights gravity to buy time. The greater galactic environment feeds this gauntlet in ways both gentle and violent. Stars shed mass through winds, clusters rattle past and sling material, clouds approach and are tidally teased into streams that lengthen and fragment. Some pieces spiral inward on timescales of thousands of orbits, some are flung back outward, warmed and restructured. Even the wider galaxy joins in as the bar structure of the Milky Way channels gas toward the center, over millions of years setting the stage for long, quiet stretches punctuated by seasons of renewed activity. The National Aeronautics and Space Administration, the European Southern Observatory, and their partners weave this portrait out of data taken night after night, year after year, pressing through the dust with patience rather than force. Their instruments do not merely see, they time. Motions are recorded periods, measured slight shifts in speed and position, noted until patterns emerge from what first seemed noise. A star deviates a tiny fraction from a smooth orbit. A cloud brightens ahead of a bow shock. A filament wavers along its length in a wave that crawls over years. Each detail adds a thread, and the threads braid into a vision of a central machine governed by gravity, but tuned by magnetism pressure and the fossil record of past storms. The mystery deepens not because the map is empty, but because the map is full. The center of the Milky Way is both a cauldron and a clock fired by processes that build and unbuild structures calm enough for complex molecules to persist in shielded pockets, harsh enough to strip electrons from atoms a breath away. The monster at the center is not yet named here, not yet described in full, but its influence already shapes every description. It is the reason stars can race without flying apart. The reason gas gathers into rings instead of rain, the reason light lines bend into arcs that sketch an invisible well. The hidden core is therefore not only a place, it is a task the galaxy has set for those who would understand it, to look without ordinary sight, to listen across wavelengths, to translate motion into mass and heat into history, and to accept that the nearer one approaches, the more the rules of intuition give way to the law of gravity written at overwhelming strength. Out in the spiral arms, the Milky Way feels human in its gentleness. Here in the heart it becomes truly galactic, and the first layer of the mystery is simply this realization that the galaxy keeps its greatest secret, not by emptiness, but by abundance, not by silence, but by a crowded choir of signals that must be separated and carried inward step by step toward the thing that holds them all in its grip. Long before a name is given to the dark engine at the centre, the galaxy begins to whisper in forms of light that ordinary eyes cannot use, and those whispers come first as radio murmurs that move through dust without care. In the early decades of the 20th century, engineers hunting down static for transatlantic communication stumble on a steady hiss that rises and falls with the sidereal day, and careful measurement shows that the loudest part of this hiss lines up with the constellation Sagittarius, the direction of the Milky Way's heart. A few years later, a patient observer builds a dish in his yard and maps the radio sky by hand, sweeping the heavens night after night until a band of radio brightness traces the plane of the galaxy like a scar seen by touch alone. That band swells near the centre, swelling not with the soft thermal heat of warm gas, but with a harder kind of glow that arises when fast electrons spiral around magnetic fields and shed energy in long, forgiving wavelengths. The map is crude by modern standards, a rough drawing of a face only half known, yet the message is already clear: the hidden core is not quiet. It has made an imprint that even a backyard instrument can trace. The reason those wavelengths succeed where visible light fails is simple and material. Dust built from tiny grains of carbon and silicate eats visible light and re-emits it as heat. But radio waves carry lengths that are far larger than the grains and pass through with little loss. The galaxy is in this band transparent, and through that transparency the central bulge stops being a blind spot and becomes a laboratory. As radio astronomy grows from backyard curiosity into global practice, the sensitivity improves, the antennas grow wider, and the maps sharpen. Astronomers begin to separate components within the bright band thermal emission from ionized gas mixed with non-thermal radiation, from populations of energetic particles, and within this structure the brightest region holds. It is not yet a point, not yet the compact peak that will later be named, but it is already a knot of unusual power. At the same time, optical astronomers find that there are rare places in the central sky where the dust thins a little, where star fields in the bulge can be seen with ordinary telescopes during moments of exceptional steadiness. These windows do not show the central furnace itself, but they reveal a crowding of stars that argues for enormous mass in a small volume. This, paired with radio brightness that refuses to waver with earthly weather or human schedules, suggests that some abiding engine works behind the curtain. The push into infrared begins as technology improves. Detectors that can count heat instead of light are carried to high mountain tops, then to the stratosphere on balloons, then above the atmosphere entirely, and they return a new kind of image. They see warm dust glowing like fine embers all through the central regions, embroidering the bulge with lanes, filaments, and knots that reveal shock fronts and stellar nurseries. The infrared sky around the centre is not a uniform haze. It is an uneven terrain where rivers of dust and gas slip around the gravity wells of star clusters and are deflected by magnetic tension into patterns that visible sight cannot guess. In the longer infrared, the cool outer layers of giant stars stand out. In the shorter infrared, the hottest dust and the most recently formed stars draw the eye, and the eyes, now tuned to heat, agree with the radio maps on one important point: the middle is crowded and restless. Early high-energy observatories add another dimension. The first X-ray satellites show a sky filled with violent points and soft glows, and while the brightest sources live in other constellations, there is still a persistent hardness to the region around the centre, a reminder that collisions and shocks do not stop there. Hydrogen recombination lines measured at radio wavelengths describe clouds of ionized gas that hang like lanterns around massive stars and those lanterns mark the outlines of arcs and shells that seem to circle something they never quite reveal. The pattern of arcs hints at a ring, a circumnuclear structure that sweeps material into an orbiting corral a few light years from the middle. The ring does not prove the shape of the thing it encircles, but it does prove the presence of a deeper attraction whose reach sets the scale of the inner traffic. Interferometry, a technique that ties widely separated antennas into a single instrument, arrives next. When two dishes observe the same radio source from distant points on Earth and combine their signals, the resulting resolution climbs beyond what any single dish can manage, and when an entire network is brought to bear, individual knots within the bright central region begin to resolve. The diffuse glow breaks into finer threads. Emission stretches along narrow filaments that run for dozens of light years in almost straight lines, too tidy for mere turbulence and suggestive of magnetic order. Among these threads are patches that flare and dim not regularly, not with the calm of a clock, but with the changeable pulse of a place where energy is stored and released through processes that still resist exact accounts. The early picture is a stack of conclusions that do not yet meet in a point. Radio maps say the center is powerful. Infrared images say the center is warm and dense. High-energy surveys say the center hosts shocks and rarefied violence. Magnetic tracers say the center is threaded by structure. And optical windows say the bulge is packed with stars. Each layer matches the others just enough to signal that they are touching different sides of a single machine, and yet each layer adds a question it cannot answer. Why are some filaments straight while others curl? Why do certain knots brighten and fade without a clear trigger? Why does the ring appear stable on long timescales, when the flows feeding it are messy and perturbed? The agencies and observatories that carry these instruments keep returning to the same sky with patience. The National Aeronautics and Space Administration lifts infrared eyes above the atmosphere and returns maps whose contours can be compared from year to year. The European Southern Observatory steadies ground-based mirrors with adaptive optics that correct for atmospheric turbulence and turn near-infrared star fields into crisp arrays where motions can be measured. Radio arrays grow spanning continents, and they begin to time the flickers of compact sources with the precision that converts brightness, changes into physical scales. The emerging story is still only a silhouette, yet it already feels like the outline of a deep well. The core is brighter in radio than the surrounding bulge by a heavy margin. The dust lanes around it are warmer than their distance from ordinary star clusters can explain. The arcs and shells of ionized gas appear to be shaped by collisions and winds stronger than any one cluster could sustain alone. This convergence makes a simple claim: there is a concentration of mass at the center, large enough to organize the environment far beyond its literal boundary. The exact nature of that mass remains unnamed in this early phase of discovery, but its fingerprints are everywhere. The timing of radio flickers constrains the size of the region that can produce them, pointing to a scale far smaller than any visible cluster. The persistence of straight magnetic filaments across noisy surroundings hints at a central dynamo that imposes order despite constant stirring. The density of hot stars in the inner few light years implies a gravitational well deep enough to hold on to the survivors of many generations of formation and death. Even without a direct image of an event horizon, the weight of the center begins to be felt, not as a single measurement, but as a consensus across wavelengths and methods. What is most striking about these first clues is how little spectacle they require. The signs are not grand eruptions or tidal waves of light that sweep the sky. They are careful increments, small deviations that agree across independent tools and point inward. A hiss aligned with the sidereal day, a band that swells near Sagittarius, a warm ring that refuses to disperse a handful of straight filaments that do not bend to local disorder, a timing curve that is too quick for anything but a tiny intense source. Piece by piece, the invisible city at the galactic center begins to glow in human understanding, and while it still keeps its true layout hidden, it no longer looks like an ordinary urban thicket of stars. The conclusion is not yet spoken, but the path toward it has been set. The center holds something small, heavy, steady, and quietly forceful enough to command gas dust stars and fields. The first clues do not declare the monster. They make the surrounding neighborhood reveal that it is governed, and that is how the mystery deepens before a name is even attached. In the middle years of the 20th century, the radio glow of the galactic center is still a broad, complicated patch, a quilt of knots and filaments that refuses to yield a single culprit until a set of careful measurements begins to separate the voices inside the choir. Astronomers point increasingly sensitive antennas toward the heart of the Milky Way, and use a method that links dishes across large distances so that their combined sharpness acts like an Earth-sized lens. With this reach, they start to peel the region apart. The wide haze resolves into a complex known as Sagittarius A itself, a tangle of shells and arcs where ionized hydrogen gas shines, and supernova scars still warm the radio sky. Yet within this tangle a smaller note keeps rising. It is compact, it is bright for its size, and it lives in exactly the place where gravity ought to culminate if the galaxy's mass is arranged as the motions of stars suggest. The source earns a distinctive designation, Sagittarius A star. The word star does not claim that it is a normal star. It simply underlines how sharp and point-like it appears within the messy background, like the head of a pin against a brushstroke. What makes this compact voice remarkable is not only its brightness, but also the way it behaves under scrutiny. When the linked antennas measure its apparent size at different radio wavelengths, the measured diameter swells in a way that can be traced to scattering by irregularities in the interstellar medium, much like the way a candle seen through frosted glass appears larger and blurrier than it really is. After accounting for that blurring, the intrinsic source remains astonishingly small. At short radio wavelengths, the size limit collapses toward a scale comparable to the very innermost region, where light can still skirt a deep gravitational well, in a sky filled with clouds and remnants that measure many light years across this tiny core sights as a stubborn, almost point-like ember suggesting confinement by gravity that ordinary star clusters cannot supply. Precision timing brings a second surprise. In place of a steady beacon, the compact source flickers. It brightens and dims on human timescales, sometimes on the order of hours, an impatience that cannot be produced by any structure larger than the distance that light can cross in that time. That distance is tiny by galactic standards, a realm measured in the span of the inner orbits that would surround a compact mass rather than the loosened scales of a star-forming cloud. The very fact of change thus becomes a ruler, and that ruler points to a region whose size is measured in fractions of a light day, a scale that nudges close to the boundary where gravity traps light itself. The position on the sky adds weight to the argument. The compact source sits within a fraction of an arc-second of the dynamical center, defined by the motions of stars in the bulge. It does not drift as a foreground object would. It does not parallax with Earth's orbit the way a nearby source would. It is fixed at the focus of the galaxy's motions as if a string were tied from every star to a shared point, and the knots all tightened there. This coincidence would be extraordinary if it were chance. It becomes persuasive when taken with the size and variability. Together they lock the attention of observers who return season after season to check if the ember behaves like a living engine or a trick of the light. The spectrum is another clue. Ordinary thermal sources like clouds whose particles glow with heat produce a gentle curve of brightness that falls in a predictable way with frequency. Sagittarius A star refuses to follow that curve. Its brightness rises more steeply towards shorter radio wavelengths than warm gas alone can explain, pointing to a different process in which fast electrons spiral around magnetic fields and shed energy. Such non-thermal radiation is plentiful in supernova remnants and jets from active galactic nuclei, but those structures spread over large scales and show clear shapes. Here the emission is packed into a space so small that the energy density must be extreme and the means of producing and containing that energy narrow. Either there is a compact object of enormous mass that cages the plasma in its grip, or there is a new unimagined configuration that hides behind the same mask. The radio maps of the larger Sagittarius A complex provide helpful context. They show arcs that bow, as if a wind or shock pushes them from the inside threads that appear to drape over an unseen scaffold and cavities where hot gas has carved space. These forms would be puzzling if the center were empty. They become coherent if a central engine has in past epochs heated, stirred, and in places sculpted the local medium. X-ray observations add a faint but important background. A low-level fog of high-energy light swaths, the central few light years, and here and there small spikes erupt, where winds collide or where matter plunges into shocks. The compact radio core sits in the middle of this busy neighborhood, like a furnace seen through the walls of a workshop. Even when not blazing, it radiates enough to mark the heart, and when it flares, the whole room answers with echoes and brief afterglows. As the technique of linking far-flung dishes improves in the late 20th century, observers make one of the most decisive measurements. They track the apparent wander of the compact source across the sky over many years, and find that it barely moves at all once the rotation of the sun around the galaxy is subtracted. If it were a star, its orbital speed in such a strong gravitational field would smear its position. If it were a chance overlap of smaller objects, their relative motions would blur the centroid. Instead, the source stands nearly still, as if its inertia were enormous. The simplest path to such stillness is great mass concentrated in a tiny region. That mass need not be active in the violent sense of a quasar to dominate its environment. Even a quiet, underfed engine of that scale would command the nearby stars and gas. The era around the recognition of Sagittarius A star thus marks a turning point. Before it, the galactic center is a large, interesting area with many overlapping processes and no single master. After it, the region has a center that behaves like an anchor. The designation does not solve the mystery, it organizes it. Now, variability can be understood as potential feeding from clumps and filaments that stray too near. Now, straighter magnetic filaments can be viewed as structures that align with field lines shaped by the rotation and charge of a compact engine. Now, the circumnuclear ring takes on the role of a reservoir rather than a mere curiosity, a storehouse that sends inward a steady trickle punctuated by brief torrents. And yet, even as order grows, the source refuses to reveal a surface or a solid outline. There is no disk to watch turn, no shell to map and call a boundary. There is only radiation from plasma that dances in a gravity so strong that time and light behave with noticeable strain. That strain will later be measured with stars that swing close enough for their spectral lines to redden, as general relativity predicts. But for now, the case rests on a stack of radio facts, a source that is very small, very central, very reluctant to drift, and very quick to change. The galaxy has at last a named ember in the hearth. Whether it is a star, a cluster of exotic remnants, or something deeper, is the question that this section leaves smouldering. The evidence favours a single massive engine, a compact well whose pull writes order on the surrounding chaos, but the final shape of that well remains to be traced by sharper eyes and more exact clocks. For the moment, the name Sagittarius A star is less a label of certainty than a marker on the path, a sign that the search has narrowed from a sprawling district to a single door whose threshold draws all the traffic of the inner Milky Way. Astronomers turn from maps of glow and whisper to the motions of single stars, because nothing speaks more clearly about gravity than the paths of bodies that must submit to it, and in the near-infrared, where dust yields a small company of bright points emerges around the exact centre of the galaxy. At first they appear as a crowded sparkle without pattern, but with patient timing and sharper optics, they separate into individuals whose positions can be marked night after night, season after season, until lines of motion draw themselves on the sky. The technique evolves through speckle imaging and then adaptive optics as mirrors learn to bend against the trembling of air and stitch a steady picture from moments of clarity. On the high plateaus of Chile and the peaks of Hawaii, telescopes measure the same field with complementary strength, each year coming back to the central arc second and laying down fresh points on long, careful plots. The stars closest to the centre reveal themselves as sprinters. Their tracks are not straight, but curved, not leisurely, but quick, and the curves fit ellipses that close in on an unseen focus. Among them, one star stands out for a cycle short enough to watch within a scientific career. Observers call it S2, a blue-white beacon that swings from a far reach to a near rush, and back again in roughly 16 years, threading an oval that shrinks to a few light days at its tightest pass. Near that closest approach, the star sprints at thousands of kilometers per second, a speed that defies any ordinary cluster of remnants or dense knot of dark matter. By fitting the orbit with the equations that describe motion around a dominant mass, the total at the focus is revealed several million times, the mass of the Sun crowded into a region smaller than the path of Neptune and even smaller than the path of Mercury, a concentration for which astrophysics holds one natural explanation. The conclusion is bold in its simplicity. Only a black hole can be that heavy and that compact without shining like a star or collapsing into something else that fragments and spreads. The case gains strength not merely from S2 but from her fast neighbours, each with its own ellipse, each pointing to the same focus within a tiny region. The orbits are tipped at various angles, some stretched and some rounder, but their shared centre persists through the geometry, a mathematical nail hammered into the sky. Even the changing speed along each orbit fits the classical expectation that a body moves faster near the focus and slower at the far end, as though an invisible hand tightens and loosens its grip along the way. Precision spectrographs add a further layer by splitting the light of these stars and measuring minute shifts in wavelength. As Stu dives, her spectral lines slide to the red more than they would from motion alone, an extra weight that appears when light must climb out of a deep gravitational well. In the year 2018, during a close passage, this gravitational redshift is measured in step with predictions from the general theory of relativity. The effect is small, but it is systematic and timed, and it arrives exactly where and when the theory says it should. During the same passage, careful astrometry hints at a forward twist of the orbit known as periapse precession, a slow turning of the ellipse within the plane of motion that results from the curvature of space-time itself. The angle is slight, the measurement difficult and the error bars honest, but the trend aligns with the idea that Newton's clean ellipses are not the final word when gravity becomes strong. The gravity interferometer on the Very Large Telescope pushes the story inward once more by tying together the light from multiple mirrors and imitating the sharpness of a much larger instrument. With that reach motion on scales of tens of microarc seconds can be traced, and during flares from the compact radio and infrared source patterns in the polarization and timing, suggest that hot plasma orbits very close to the point of no return, as if bright knots were circling just outside the edge where light would be lost. These measurements do not show the horizon directly. They reveal its influence through the choreography of nearby matter. That choreography is exacting. If the hidden mass were spread in a cluster of dead stars or faint remnants, the orbits of the far stars would wobble and wander under many slight pulls, and close passages would produce gravitational nudges that add up to a noisy pattern. Instead, the tracks remain clean to the limit of measurement, closing neatly and repeating with predictable cadence, except for the small relativistic twist that is itself a signature of smooth central dominance. Over time, even tiny departures are checked for signs of additional actors. A passing intermediate mass black hole would tug on the orbits. A swarm of compact objects would scatter the stars into new inclinations. A ring of dark matter would add a subtle extra pull. So far, the data say that if such companions exist, they must be modest in mass, or far enough away to leave only whispers. The mass at the center behaves like a single deep point, and that is the essence of a black hole in the language of orbits. The measurements grow more intricate as teams improve calibration, reduce distortion from Earth's atmosphere, and observe over longer baselines. Distances within the center are refined by tying the stellar motions to the absolute scale of the galaxy, and the mass estimate of the compact object stabilizes at a few million solar masses, with uncertainties that shrink as another cycle of S2 is completed. Even the subtle influence of extended matter around the hole is bracketed, limiting the amount of unseen mass that could be lurking in the inner light year. The stars become not just proof, but tools test masses that chart a potential well and expose its profile. Meanwhile, their very existence raises questions. How do such young, massive stars form in a place where tidal forces should shred any calm cloud before it can fragment into seeds of new suns? Did they form in a disk already close to the center, their birth protected by the same geometry that drives their orbits now, or did they form farther out and then migrate inward in a shepherded pack? Their presence tells of a recent episode of star formation near the monster, a heartbeat in the life of the core that adds to the sense of a living, changing environment, rather than a frozen monument to gravity. The plot tightens as fainter stars with even shorter periods are found, their swift cycles offering the hope of measuring relativistic effects with greater precision and perhaps catching the subtle frame dragging that would betray the spin of the hole itself. If the central mass rotates space-time near, it should be dragged around like syrup around a spoon, and the plane of a close orbit might twist in response. Detecting that twist requires patience measured in many periods and an accuracy that pushes instruments to their limit, but the prospect draws observers onward. Through all of this, the essential picture holds steady. The stars that circle nothing visible draw ellipses about a point that holds several million solar masses within a space smaller than a planetary orbit. Their light reddens as they dive and regains its natural hue as they climb, matching the predictions of curved space-time. Their ellipses turn slowly in the manner expected around a compact dominant mass. There is no surface to illuminate, no solid sphere to watch in silhouette, only a center that reveals itself by the rule it imposes. The galaxy has offered in these orbits a direct measurement of the invisible. It is not a metaphor to say the stars circle nothing. It is a simple report that the thing they circle cannot be seen. Its presence is written in speed and curve, in timing and colour, and in the stubborn agreement of independent teams and instruments across decades. Where once a radio ember merely hinted at a hidden engine, the dance of S2 and her kin now draws its boundary with gravity's ink. The mystery does not end with this proof. It deepens in a new direction toward questions of spin feeding and history, but the core claim stands on its own legs. A supermassive black hole sits at the centre of the Milky Way, and these bright runners are its signature. Mass is the simplest description of the monster, and also the most arresting because the value that falls out of the orbits is at once compact in space and enormous in consequence. The swift stars near the centre write an equation with their motion, and that equation points to a mass of roughly 4 million times the mass of the Sun packed into a region smaller than the path traced by the innermost planets. To imagine such a concentration is to picture gravity pressed into a single well so steep that nothing with too little speed can climb out. The proof is not a single measurement, but a chorus that agrees. Each star that threads an ellipse through the central arc second places the focus in nearly the same spot, and each fit of speed and distance reinforces the same total. The orbits are clean, the periods are short, and the centre they describe can neither be a loose crowd of remnants nor a cloud of unseen matter spread across a wide volume. It must be small, heavy and smooth in its pull. A second line of evidence speaks with equal calm. The compact radio source sits almost exactly at the dynamical centre, defined by the stellar motions, and it does not drift in the way a lighter object would. After the motion caused by the Sun's own journey around the galaxy is subtracted, the residual wander corresponds to only a few kilometres per second. In a crowded environment where nearby stars tug and jostle, near stillness demands great inertia, and great inertia demands great mass. The conclusion is spare and powerful. The Milky Way's core holds a single deep point whose gravity can rule the inner light year with a steady hand. For such a heavy engine, one might expect brilliant light, yet the centre is faint by the standards of active galaxies. This is the first paradox the mass creates, and it becomes a clue rather than a contradiction. When gas falls toward a compact object, it does not drop straight in. It swirls into a disk or a puffed flow, and friction within that flow turns orbital energy into heat. Bright, rapidly fed engines radiate that heat with furious efficiency, lighting up the sky with ultraviolet and X-ray glare. The core of the Milky Way does not behave that way. It is underfed, and the flow that approaches the horizon is thin and hot, with particles that do not share their energy well. Heavy ions carry most of the heat, but the light electrons are the ones that radiate. When energy does not pass quickly from ion to electron, the glow stays low. Much of the heat is dragged inward and lost behind the horizon, rather than converted into light. The result is a lean engine whose mass is vast but whose current meal is small, and the faintness becomes a signature of this inefficiency rather than a puzzle to be explained away. The size scales involved help the mind hold both the weight and the quiet at once. A non-spinning black hole with 4 million solar masses would have a point of no return at roughly 12 million kilometres from its centre, a sphere that would fit comfortably within the path of Mercury if placed inside the solar system. Most of the observed radio and infrared light comes from gas and electrons whirling outside that boundary, within a few tens of those radii where gravity is still strong enough to wrench light into arcs, and to slow clocks in ways that careful instruments can detect. The linked network of radio dishes that forms a planet-sized eye delivers a ring-like image whose thickness and brightness pattern suggest a hot magnetized flow just beyond the final drop. The darkness inside the ring is not a physical surface. It is the absence that light reveals when its paths are bent away or pulled inward. The mass sets the ring's scale, and the measured ring matches the mass that the orbits demand. The same mass governs the broader neighborhood. There is a reach around the center where the black hole's gravity wins over the random thermal push of the hot medium, a sphere within which gas can be trapped, unless turbulence or pressure blows it back out. Inside that reach, the flow fights with its own spin. Angular momentum keeps matter in orbit the way a skater's spin keeps arms extended. To fall inward, the gas must shed that spin. It does so by rubbing against itself, by breaking into eddies that exchange momentum, and by coupling to magnetic fields that drag angular momentum outward along twisted lines. When the process is slow, matter hovers in a hot dilute state and radiates little. When a clump or a filament tips the balance, a brief brightening follows as fresh fuel reaches tighter circles and heats more strongly. The mass thus frames both the quiet and the flicker. It also organizes the visible order in ways that seem at first surprising in such a turbulent place. Within a few light years, the winds of massive stars crash into one another and form shells whose bows face away from the center, as though the pressure there sets a steady direction. Young stars far younger than one might expect so close to a tidal field, this strong trace partial disks and streams, whose alignments may record the geometry of the gas from which they formed. Their very youth poses a question. The mass sharpens. How did star formation proceed in a region where gravity shears clouds and heat and radiation push back? One answer is that a dense ring or disk briefly gathered enough to fragment despite the tides, helped by shocks and by the very compression that the central mass encourages. In this way, the weight serves both as threat and as midwife, a dual role that the present star cluster seems to remember. The measured mass also squeezes alternatives to a point. A cluster of dead stars crammed into the necessary volume would scatter itself through countless small kicks and would not remain stable over many millions of years. It would impart extra jitters to the fast orbits that careful timing would detect. Exotic concentrations of unseen matter could be imagined, but their equations either forbid the required density or predict other signatures that are not seen. The simplest path through the evidence remains a single deep well with an event horizon, a supermassive black hole whose smooth potential explains the clean ellipse, and whose small size explains the tight limits set by rapid variability. The mass does more than answer what the center is now. It points toward what the center has been. Light echoes on distant clouds imply that a few hundred years ago, the core shone more strongly perhaps because a larger dose of gas reached close, or because a small jet briefly stirred and then faded. The echoes fix the time and hint at the energy, and the mass frames those hints by telling how much fuel would be needed to produce them and how long a surge could last before the storehouse emptied. When future clouds drift inward, or when a fragmenting stream delivers a new parcel, the same mass will again set the pace at which the core can convert gravity into light. In this sense, the number is a prophecy. It says that long quiet will likely be the rule, punctuated by seasons when the ring brightens and the inner flow quickens. Everything in the central few light years answers to the weight. It bends the paths of stars, shapes the lanes of gas locks, magnetic filaments into large-scale order, and sets the terms under which matter can fall, heat, and shine. It explains a dim core in a place where many would expect glare, and it frames the outbursts that sometimes surge from the quiet. It points to the ring seen by the largest eyes and to the reddening measured when a star dives and climbs. It is both solution and prod because once the mass is known, new questions sharpen rather than soften. How fast does the central object spin? How exactly does the flow change from a thin luminous disk to a hot thrifty puff? How does the present calm compare with the stronger seasons recorded by echoes? The number does not end the story. It fixes the scale on which the next mysteries unfold. The core of the Milky Way spends most days in a state that looks like restraint, a low glow where the radio and infrared light trickles rather than roars, and then without warning it flares. The pattern is not periodic like the steady pulse of a clock. It is irregular, a scatter of brief awakenings that rise over tens of minutes and fade over a few hours, as if the engine breathes shallowly and then suddenly takes a deep gust of fuel. The National Aeronautics and Space Administration's Chandra X-ray Observatory has watched the core brighten by orders of magnitude in high-energy light during such outbursts, while ground-based infrared eyes at the Very Large Telescope and the Keck Observatory record synchronous spikes that climb and fall in step with the X-rays. The Atacama Large Millimeter or Submillimeter Array listens at longer wavelengths and sometimes hears a delayed echo, a slower swell that follows the fast flare like a lingering sigh in a cooler band. In quiet between these events, the spectrum and brightness suggest a hot, thin flow dribbling inward with poor radiative efficiency. But when the flares come, something changes in the inner few tens of gravitational radii, a region where gravity is strong enough to curve light and where motion bends time. The sparks point to fresh energy released close to the point of no return. One family of explanations speaks in the language of magnetic reconnection, the sudden snapping and healing of magnetic field lines in plasma that carries opposite directions of field into close contact. When twisted loops are pressed together in a turbulent flow, the tension can build until the field lines break and rejoin in a new configuration, dumping stored magnetic energy into the particles. Electrons leap to higher speeds, spiral more tightly, and radiate more powerfully in radio and infrared, while collisions and wave processes push part of that energy into X-rays. This picture matches the short rise times the polarized swings seen in near-infrared light, and the rapid variability that marks a small source region. It also fits the intuition that a weakly fed engine will store energy in its tangled fields until a threshold is crossed. Another family of ideas centers on small clumps of gas or dust that wander inward from the circumnuclear environment. A single fragment compressed by tidal forces and heated by shocks as it plunges through the inner flow can brighten as it passes a tight orbit shedding light as it is torn and diluted. If such fragments are common, then the flares become the visible signs of a sporadic diet. Each meal small but intense, each passage stirring the inner plasma into a temporary frenzy. Observations of individual flares sometimes hint at a quasi-periodic wiggle, superimposed on the main, brightening a gentle modulation that could be caused by a hotspot orbiting near the innermost stable path allowed by gravity. If so, the wiggle is a stopwatch that times motion close to the edge. The gravity interferometer working at the Very Large Telescope has tracked the position of infrared flares with exquisite precision and seen loop-like motion on the sky that suggests compact blobs circling in orbits only a few light-hours across. The details are still debated, but the pattern is alluring. A knot of energized plasma orbits cools, spreads and fades, leaving the engine dim again until the next knot forms or the next reconnection tears through the field. The calm state is no true rest. It is a dynamic equilibrium where hot ions carry most of the thermal energy, electrons remain cooler and radiate only modestly, and magnetic stresses hold much of the free energy in twisted shapes. Outflows may carry away a portion of the inward drift, pushing back against gravity and starving the inner zones further. Into this balanced scarcity, a small trigger can cause a noticeable surge. A star's wind may thicken temporarily. A filament may thread a narrow channel toward the center. A wave in the disk may steepen and break. Any of these can concentrate fuel or tighten fields until a threshold is crossed and a flare begins. Because the inner region is so small, light crossing times are short, so rises and falls can be swift. Because orbits near the edge are fast, any structure bright enough to be seen can be carried around a few times before it cools, imprinting a brief rhythm on the light curve. The consequence is a catalogue of flares that each look similar in outline yet unique in detail, like waves on a shore shaped by the same tide but coloured by local stones. The quiet between outbursts hides a longer story of past vigour. X-ray echoes reflected by clouds hundreds of light-years from the centre reveal that a few centuries ago the core shone far more brightly for a time, as if a larger meal or a faster reconnection cascade lit up the inner flow. Those ghosts of light reach Earth today with a delay set by geometry, and they hint that the present season of flickers may be a low tide in a cycle that rises and falls over centuries. The same mass that stabilizes the orbits of stars sets the clock of this cycle by controlling how quickly gas can lose angular momentum and fall inward. A large inflow will not arrive in a single rush. It will fragment shear and sometimes stall. When a piece reaches close, the core lights, then fades as the piece is swallowed and the next waits its turn. Into this picture, several memorable events have been folded. A compact object known by a short label drifted toward the center. About a decade ago appeared to stretch near closest approach, and then passed by without the enormous flare some had anticipated. The lesson was not a failure, but a refinement. The inner flow is resilient. The amount of true fuel can be less than a cloud's outer appearance suggests, and not every close pass guarantees a storm. The watch continued, and soon after a different flare rose to a record intensity in the near-infrared, reminding observers that while predictions are shaped by models, the engine keeps its own counsel. The instruments that keep this vigil have learned to talk to one another. When a rapid brightening appears in the infrared, alerts go to X-ray and radio facilities, so that spectra and timing can be caught across bands. Polarization is measured to trace the direction and strength of magnetic fields and how they turn during the event. The result is a growing library of flares with multiple views that can be compared against the competing pictures. Do the strongest events carry a clear polarization swing as a hotspot circles? Do the radio echoes always lag, pointing to cooling and expansion? Does the X-ray tail match the shape expected if electrons upscatter lower energy photons in a dense inner bath? Each new flare answers a little and adds a little, and over years the quiet state itself becomes better defined by the structure it returns to after each outburst. What is most striking taken together is that the calm and the flares are not opposites. They are two faces of the same low-feeding regime. The calm is the average of many small rearrangements that do not cross the threshold of visibility, while a flare is a rearrangement that does. The underlying engine remains the same, a deep gravitational well, a hot and dilute plasma-tangled magnetic fields, and a supply line that is thin and irregular. The monster is quiet because it is starved, but it is not sleeping. It turns its limited fuel into short bursts of radiance with the efficiency of a craftsperson who cannot waste a scrap. This behavior is not embarrassing for a supermassive black hole. It is instructive. It shows how gravity can dominate while light remains modest, and how a galaxy's heart can influence its environment through many small pulses rather than a single unending blaze. The next section will follow the threads of magnetism that hold so much of this energy in reserve, because within those threads the calm is woven, and from those threads the flares are torn. Magnetic fields in the galactic center are not decorations on a violent sky. They are the quiet structure that lets chaos hold a shape. In wide radio images across the inner few hundred light years, narrow filaments stand like taut wires, some extending for tens of light years, with almost no bend, glowing with non-thermal radio light, because fast electrons spiral along lines of force. Such straightness is startling in a place filled with shocks, winds from massive stars and turbulent wakes from supernova remnants. The simplest reading is that a large-scale magnetic order underlies the bustle strong enough to resist ordinary stirring and steady enough to survive for long times. Polarization measurements strengthen this view. When radio and millimeter light is split into its preferred directions, it carries the imprint of a field that sets those directions, and in the central regions the pattern is neither random nor uniform, but a mosaic of aligned patches that together suggest a coherent field threaded through the clutter. In some places the field appears to run roughly perpendicular to the galactic plane, as if vertical strands pass through the center like a loose bundle of threads. In others it curves as if wrapped by rotation or pushed by outflows. The field is invisible to ordinary sight, but its presence is written wherever charged particles march in step, wherever dust grains align like tiny compasses, and wherever light rotates its plane of polarization while crossing a sea of electrons. That rotation, a measurable twist in the polarization angle, is especially telling. It grows with both the density of electrons and the strength of the magnetic field along the path. Toward the center, the twist is extreme. By pairing those rotations with independent estimates of density, observers infer that the magnetic field near the core is not weak. This conclusion receives a dramatic confirmation in the last decade, when a highly magnetized neutron star is found close to the center. Its radio pulses arrive having wound their polarization by an enormous amount, far beyond the values seen along most other directions in the galaxy. From this, the product of density and field strength must be high, and since the density can be bracketed, the field is left to carry much of the burden. A strong field is not a curiosity. It is a force that shapes the flow of gas, the paths of particles, and the pace at which the core feeds. Closer to the compact source within a few light years, the magnetic story changes scale from filaments tens of light years long to loops and braids on sizes that would fit within the solar system if the system were set down at the center. The Atacama Large Millimeter or Submillimeter Array sees polarized millimeter light from dust and electrons that align or spiral with the field. The gravity interferometer on the Very Large Telescope measures fast swings in the polarization of near-infrared flares. Radio interferometers time the brightness and polarization of the compact core with precision that turns minutes into frames of a movie. During bright near-infrared events, the polarization angle sometimes swings smoothly as the flux rises and fades, a pattern that suggests that a compact knot of energized plasma orbits the core while its local magnetic field turns with it. When the knot shears, cools, or is swallowed, the light relaxes and the angle steadies. This is not proof of a single geometry, but it fits a picture in which the inner flow is strongly magnetized and in which field lines are wound and unwound by motion near the edge. The flares themselves may be acts of magnetic reconnection, where lines of force snap and rejoin, dumping stored magnetic energy into electrons that then radiate in infrared and X-ray bands. Such releases are brief, local and intense, matching the observed rise and fall times, and they happen where the field is strongest just outside the point of no return. In that same inner zone, theory and computer experiments show a further possibility that a strong field can reach a magnetically arrested state. In such a state, enough magnetic flux is dragged inward that the field pushes back on the inflow, squeezes gas into narrow lanes, and can even tap rotational energy from the compact object if the field finds purchase on the spinning space-time. The ring imaged by the planet-sized radio array is consistent with a hot magnetized flow whose field sets the thickness of the emitting region and helps create the lopsided brightness by steering how electrons move and radiate. The darkness in the middle is not a surface, it is the absence created when light paths bend inward. The brightness around it is the visible remainder of a battle among gravity rotation and magnetism just outside the final drop. Magnetic fields also provide the missing hand that removes angular momentum from gas so that it can fall. In a hot collision, poor plasma ordinary molecular friction is negligible. Instead, magnetic stresses link inner rings to outer rings, moving angular momentum outward and mass inward. This redistribution can be smooth when the inflow is slow, or burst-like when reconnection cascades through the inner flow. Part of the stored energy leaves as waves. Part of it powers winds that rise from the disk and carry away both matter and spin. In this way, fields both feed the core and starve it by letting some gas cross inward, while flinging other gas outward before it can reach the horizon. The balance between these channels helps explain why the core can remain faint on average, and yet capable of sharp brief brightenings. Farther out on scales of thousands of light-years above and below the galactic plane, giant lobes seen in gamma rays and radio rise like two soft balloons. Their sharp rims and smooth insides hint at an episode when energy from the center inflated cavities in the surrounding halo. If that episode was driven by a brief jet or a strong wind, magnetic fields would have helped confine and shape the lobes, and they likely still thread the bubbles, channeling particles and delaying their loss. Thus, the magnetic story extends from the horizon to the halo stitching, quiet present behavior to an active history. What remains open is the precise geometry near the horizon and how it changes with time. Does the inner field typically settle into a shape set by the spin of the compact object tilted slightly by the angle of inflowing gas, or does it flip and knot whenever new material arrives from a different direction? Do the long straight filaments record a single ancient combing event, or are they renewed by steady gentle outflows that keep them taut? Are the brightest flares caused when reconnection cuts through a field that has been wound too tightly by orbital shear, or when a small clump rams the inner flow and twists the field into a sudden knot? Future arrays that watch polarized light on the timescale of minutes will follow the field's turns as a flare climbs and falls, while long campaigns at radio wavelengths will track whether filaments grow drift or fade. For now, the magnetic portrait explains paradoxes that otherwise would remain stubborn. The center is ordered not in spite of turbulence, but because fields channel turbulence into patterns. The core is faint not because there is no energy, but because much of the energy is stored in fields or carried away in winds. Flares are not departures from the quiet state. They are the quiet state made briefly visible when magnetic storage reaches a threshold. The monster's mass pulls space-time curves and orbits obey. Yet the choices within that pull where gas lanes form when a flare snaps how a wind rises belong to the field. In that sense, the galactic center is a braided engine. Gravity supplies the fall, magnetism sets the path, and light records the compromises they strike from moment to moment as the inner Milky Way breathes. Around the central engine, the gas does not fall like rain. It gathers, stretches, collides, and loops into streams that form a ringed thoroughfare, a circumnuclear disk that circles within a few light years of the black hole. From a distance, this structure looks like a broken torus, thicker in some sectors, thinner in others, with lanes that feed inward like braided rivers at low tide. The material is cold enough in places to glow in lines that mark molecules and dust, and warm enough elsewhere to shine as ionized arcs traced by fast electrons. The ring is not smooth. It is a patchwork of clumps linked by filaments that shear and recombine under gravity pressure and magnetic stress. The Atacama Large Millimeter or Submillimeter Array maps this roughness by following emission from dense gas traces that thread the inner few light years, while near-infrared instruments pick out hot knots, where shocks and radiation have heated dust to a dull glow. Together, the views show a system that tries to be a circle, but cannot help behaving like weather. Collisions are the first sculptors. When two clumps meet at different speeds, or along slightly different planes, they compress each other and drive shocks that heat and ionize the gas. Compression can, for a short while, raise density to the point where molecules that would usually be torn apart can form or survive inside shielded pockets. Then radiation from young stars and the harsh field near the core strips the fragile pieces away again. In this tug of war, shock fronts fold and ripple, and the ring acquires a rim of bright arcs that seem to face the center like the bows of boats, each one a sign that outward pressure and inward gravity are meeting at a line of balance. Magnetic fields provide the second sculptor. The ring's lanes carry charge and thus feel tension along lines of force that drape the structure in a slow, unseen net. When a clump tries to slide past another, the field can link them like a loose rope, allowing angular momentum to pass along and changing which parts speed up and which slow down. Over time, these exchanges act like a brake on the outer lanes and a push on the inner ones, letting some gas shed spin and drift inward, while other gas is flung slightly outward. The result is not a steady conveyor, but a series of deliveries parcels of mass that spiral inward, stall, and sometimes resume after a pause set by local conditions. Within the ring, several streamers wind toward the center, as if drawn from the rim by invisible fingers. Each streamer has its own history. One may be the shredded remains of a cloud that passed too close to a dense knot and lost its outer layers. Another may be a thread pulled from the ring by a tidal resonance with the central mass. A third may be the cooled wake of an outflow that has condensed into a lane of return. Where these streams cross one another or ram into ambient gas, new shocks appear, and a fresh set of arcs and edges takes shape. The pattern changes on timescales that human observers can follow, with bright knots drifting, fading or breaking as they move inward, suggesting that the ring is not a permanent fixture, but a current arrangement in a long sequence of rearrangements. The stars within a few light years of the center add their winds to the mix. Each massive star drives a flow of particles that expands until it meets the pressure of the surrounding medium, forming a bow that points away from the center. Where many such winds gather, their collisions carve cavities and sharp rims, and the gas is stirred into turbulence that sends eddies into the ring. Supernovae, though less frequent, leave longer scars. Their blast push on the ring and open channels in its face through which material can leak inward or outward, depending on how the pressure gradients line up. In this way, stellar life and death write tracks on the same land that gravity has made, turning the inner few light years into a palimpsest of overlapping motions. The chemistry in this region carries its own story of survival and erasure. In shadowed folds of the ring complex, molecules endure for a time protected from the hard light of the center by layers of dust. Where shocks pass, the dust can sputter and release ices, seeding the gas with new ingredients. Then, as the clump rotates into a clearer view of the core, or as a nearby flare sends a burst of X-rays, and ultraviolet light bonds break and the mixture resets. Observers identify these cycles by comparing line strengths across the ring and by noting that some molecules that should not last in such a harsh environment appear in fresh layers downstream of recent shocks. It is a chemistry written in pencil on a stone table, constantly rewritten, but legible in the moment. The ring is not the only actor. It is a stage for longer flows that reach into the galaxy. The bar of the Milky Way, a long arrangement of stars and gas that crosses the central bulge, can torque gas in the inner few thousand light years and send it inward along paths that intersect the ring. When a new delivery arrives, the ring may fatten or tilt its rim, brightening where fresh material rams the standing lanes. Over many millions of years, inflow from the bar may feed episodes of star formation near the center, leaving behind clusters that later drift and disperse, while the ring reshapes for the next cycle. On much smaller scales, the streams inside the ring appear to feed a spiral of ionized gas that reaches toward the compact source, a miniature whirlpool within the larger eddy. In high-resolution radio and infrared maps, this pattern takes the form of a set of arms that twist as if feeling the gravity of the center, directly each arm marked by edges where electrons glow in response to compressed magnetic fields and shocks. The arms do not touch the horizon. They fade into the confusion of the inner accretion flow, but their direction is plain. They point at the same central nothing that the star orbits define. The dynamics of the ring and streams solve a puzzle raised earlier by the low average brightness of the core. If the engine is starved, why does so much gas sit nearby? The answer is that proximity is not the same as permission to fall. Angular momentum, the tendency to keep moving in a circle rather than slip inward, is a fierce gatekeeper. Only where collisions, magnetic stresses, or gravitational torques can transfer spin outward does material cross the small steps that lead inward. Most of the time, the ring holds its mass like a hoard, letting only slivers pass. Sometimes a richer spill occurs when a clump breaks and its fragments lose spin in a cascade of shocks. These are the moments when the core brightens the very events that observers catch as flares. The ring thus becomes both storehouse and scheduler, a reservoir that feeds in pulses determined by its own internal weather. Even the straight radio filaments that pierce the central region may converse with the ring. Where a filament intersects the disk, a bright spot sometimes appears as if particles travelling along the field line have found a denser target and glow more strongly as they pass. These crossings may help transfer energy between the large-scale magnetic structure and the local flows, stiffening some sectors of the ring while loosening others. If so, the quiet order of the filaments is not separate from the changing face of the disk. It is the scaffold against which the disk rubs. The circumnuclear region, therefore, is not a single simple object, but an ecosystem of gas and dust stars and fields. Its behavior narrows the range of possibilities for how the center feeds and how often it can awaken. It shows that quiet does not mean empty, and that the path from the ring to the horizon is long in physics even when short in distance. It shows that collisions and magnetism can carry out the work of moving spin as efficiently as a perfect thin disk would, but in bursts instead of in a steady stream. Above all, it shows that gravity's rule can create patterns even where every ingredient seems opposed to order, and that those patterns can be strong enough to hold shape for many orbits, and soft enough to break when a new delivery arrives from the wider galaxy. The next layer inward will follow these streams as they fade into the hot dilute flow that makes the glow just outside the final fall, where orbits blur into turbulence and where light begins to bend as much as it shines. Among the fast runners that circle the invisible core, one star becomes the clock and the crucible. because its path closes quickly enough that an entire cycle can be watched within a human career, and because its speed near closest approach presses physics into its strong field regime. Astronomers mark this star with a short label that matters less than its behavior. Over roughly 16 years, it traces a clean ellipse that shrinks at its near point to a distance of only a few light days from the central mass. And at that near point, its speed climbs to thousands of kilometers per second. From the curve of its path and the cadence of its motion, the mass at the focus is measured. From the color of its light at different parts of the orbit, the structure of space-time around that mass is tested. Years of steady watching made possible by adaptive optics that calm the blurring of Earth's air, and by interferometers that braid light from multiple mirrors into a sharper image yield a sequence of positions with errors small enough to reveal subtle bends and twists. Spectrographs split the star's light into fine lines that can be timed like the ticks of a metronome, and during the near passage in the year 2018 those lines slide to the red, beyond what simple motion along the line of sight would cause. The extra shift arrives exactly when the theory of general relativity says it should, because during the near pass the star and its photons are moving fast in a steep well, and time slows both because of speed and because of gravity. The measurement is not dramatic to the eye, but it is decisive in the arithmetic, and it marks the first time that a single star around a galactic black hole has been used to catch the gravitational redshift in the act. Astrometric points taken before and after the near pass add a second layer. They hint at a slow turning of the ellipse within its plane, a periapse precession that would not exist in Newton's picture of gravity, but that arises naturally when spacetime is curved by a compact mass. The angle is small, the uncertainties frankly stated, and the measurement continues to grow firmer as more of the orbit is traced, but the direction and size agree with the relativistic expectation for a mass of a few million solar masses. This is a quiet kind of confirmation, the kind that emerges not from a single spectacular event, but from patient agreement between prediction and observation over many years. The star's role as a test particle also exposes possibilities beyond the standard picture. If there were a large amount of extended mass within the star's orbit, perhaps a dark cluster of remnants, or an exotic concentration of unseen matter, then the path would deviate from a clean ellipse in ways that differ from the simple relativistic twist. Close approaches to a swarm of hidden bodies would kick the orbit, thicken the family of orbital planes, or add noise to the timing. So far, the data say that any such extra mass within the inner light year must be modest. The potential well feels smooth like that of a single object, not rough like the sum of many small pools. That constraint makes the case for a true black hole even stronger, and narrows the room for alternatives that try to replace it with a cluster of anything else. The star's brightness also changes character near closest approach, not in wild bursts, but in the way the spectrum and the apparent motion combine. When the star is far, its light behaves like that of other hot stars. When it dives, the small additional redshift and the slight bending of its apparent position by the deep potential leave subtle signatures that very precise instruments can extract. The gravity instrument at the Very Large Telescope pushes into this regime by measuring positions with accuracies measured in tens of micro-arc seconds, and by tracking polarization and intensity changes in nearby infrared flares that may arise from plasma orbiting even closer in. During the year of closest approach, brief compact brightenings appear close to the expected location of the central engine, and their apparent looped motion on the sky suggests orbiting hotspots at radii of only a few light hours. Although these features are not the star itself, their timing during the same season further tightens the link between orbit gravity and the restless inner flow. As more fast stars are found with shorter periods, the laboratory expands. There are hints of stars whose cycles may be only a handful of years, their paths so tight that the relativistic precession should become easier to measure, and in time the more elusive twist called frame dragging may enter reach. If the central mass spins space-time near, it is expected to be dragged around, so that the plane of a close orbit slowly tips the way a gyroscope's axis precesses in a turning fluid. Measuring such tipping would reveal the spin magnitude and orientation facts that would open a fresh chapter on how the black hole grew, because different feeding histories and past mergers leave different spins. That goal demands long baselines and relentless calibration. It also demands a careful account of every possible source of confusion, from unrecognized blended stars to unmodeled instrument drifts. The teams who gather these data publish not only their headline numbers, but also their error budgets and their cross-checks, because the claims sit on the edge of present capability. The accumulation of years makes the difference. With each cycle, the orbit closes more tightly around the truth, and small departures that were once buried in noise begin to stand up above the floor. Alongside these grand tests, smaller puzzles keep the wonder alive. How did such a young, massive star arrive in a place where tidal forces are fierce? Was it born in a disk of gas already near the centre, protected by geometry until gravity gathered it into a single source, or was it born farther out and later shepherded inward by the pull of a dissolved cluster? There is evidence for partial disks of young stars within a few light years, their aligned motions hinting that they share a birth history, but the details remain open. The answer matters because it ties the clean lines of dynamics to the messy history of formation in a violent place. If stars can form in situ so close to the well, then brief periods when the circumnuclear disk grows dense may seed entire families of orbits that later act as test masses. If they are immigrants shepherded inward, then the centre's reach changes not only the gas flows, but the demographics of its stellar city. Even the single star that anchors this section carries a quiet caution. It is a brilliant test because it is both bright and close, but it is also only one example. The best practice is to build a population of clocks to measure many short-period orbits, to map their precessions, to compare their planes, and to look for correlations with nearby gas streams and filaments. In time, the ensemble can reveal the spin-the-slope of any extended mass distribution, and the presence of subtle resonances that exchange angular momentum among the stars themselves. Through all this, the heart of the story remains elegant. A point of extreme mass sits at the centre of the Milky Way. A small set of stars dare to graze it at high speed. Their paths recorded with care match the predictions of curved space-time, including the extra reddening of a light as a star dives, and the slow turning of an ellipse that orbits a compact mass. The measurement does not make the monster less mysterious, it makes the mystery precise. With each pass, the theory is asked a sharper question, and for now the answers reach back from the core in calm agreement. What waits ahead are the spin-the-frame dragging, and the influence of the inner magnetic engine on orbits that pass near the place where light itself can only circle and then fall. The present quiet at the galactic centre does not erase the marks of older seasons, and in the last few decades astronomers have learned to read those marks in light that has been reflected and delayed by clouds that sit hundreds of light-years from the core. These clouds, cold and dense, act like pale mirrors for high-energy light. When an X-ray burst from the centre sweeps across them, it strips inner electrons from iron atoms and prompts them to emit a telltale line as they refill a narrow colour that stands out from the broader glow of hot gas. It also scatters the incoming light in a way that depends on the angle of arrival and the density of electrons inside the cloud. The result is a moving echo that crawls across the cloud with the pace of a spotlight sliding over a distant wall. Early hints of such echoes appeared in the closing years of the 20th century when satellites saw hard X-ray emission from massive clouds near the centre that could not be explained by local heating. In the following years, a parade of observatories, among them the Chandra X-ray Observatory XMM Newton, and later NewStar, mapped these emissions with improving clarity and watched them change over time. The iron line brightened in some clumps, faded in others, and shifted from one region to a nearby region in a way that suggested a wave of illumination moving through the cloud rather than a change within the cloud itself. By measuring how fast the bright patch travelled across the face of a cloud, and by knowing the scale of the cloud from radio and millimetre observations, teams could infer how long ago the original flash must have left the centre. The answers pointed to events that occurred a few centuries in the past, far longer than any single flare seen in modern monitoring, and far shorter than the age of the galaxy. The picture that emerges is that the central engine experienced a period or a sequence of periods when it shone with a brightness much higher than today, an active phase that then subsided, leaving the present-day core in its starved, flickering state. These echoes turn the central few hundred light-years into a natural time delay machine. Each cloud sits at a different position relative to the line from Earth to the core, and the geometry sets a different delay. When an outburst occurs, one cloud will respond sooner and another later, and in principle the moving pattern of brightening across the entire complex could be inverted to reconstruct the original light curve long after the flash has faded from direct view. In practice, the clouds are messy, the distance is uncertain and the lines of sight crowded, yet even with these limits the method delivers a rough chronicle. It says that the core was more luminous for a span of years to decades in the recent past, and that the power involved was strong enough to light up iron in clouds hundreds of light-years away. The character of the echo adds constraints on the physics of the source. The iron line is narrow, which implies that the illuminating spectrum included hard photons capable of freeing inner electrons, and the ratio of scattered continuum to line flux suggests that the flare was not simply a burst of soft glow, but included penetrating energy. The reflected spectrum looks much like what would be expected from a compact hot flow, energized near a black hole scaled up in brightness from the present low state. The behavior of the echoes over time also lets observers distinguish between two broad classes of cores. One is a change in illumination from the center. The other is a local brightening within the cloud due to cosmic ray bombardment or internal shocks. When the bright region slides across the cloud at a speed faster than any plausible sound wave in cold gas, and when multiple clouds show coordinated changes consistent with a single moving front of light, the external illumination picture wins. The measured patterns favor that interpretation strongly. In that framework, each cloud becomes a clock and a ruler. Combined with distance estimates from radio parallax and molecular line velocities, the timing pins down the position of the flare in the past, with enough clarity to say that the outburst must have occurred within the last several centuries, not millennia and not decades. This recent timing has consequences. It means that the present faintness is not the permanent default. The core can brighten by a large factor without becoming a classical quasar, and it can do so in a way that reaches deep into the central molecular zone. Such an episode would have altered gas chemistry, raised ionization levels, and perhaps triggered or suppressed star formation in parts of the ring and streams. The clouds that carry the echoes therefore also carry a record of how the central engine couples to its environment beyond the inner few light years. The scale of the past activity is still debated. Some models favor a single relatively brief burst that lasted a few years to a few decades, while others allow a few separate bursts spaced by gaps. The spatial pattern of ion line variability across different clouds holds the answer, but is subject to uncertainties in distance. What all models share is the need for a central luminosity far above the present daily level, high enough that even after scattering and absorption, a strong signal reached the clouds. Given the measured mass of the black hole, such a luminosity could be achieved if a modest amount of gas fell inward more efficiently than usual, perhaps because an unusually dense clump crossed the final barriers of spin and turbulence. Alternatively, a transient jet or a strong outflow could have lit the clouds with a harder spectrum more readily. The echoes do not uniquely identify the driver, but they demand power and timing that rule out small internal events within the clouds themselves. The same period of heightened central power may connect to larger-scale structures seen above and below the galactic plane, where lobes of gamma-ray and radio emission rise like faint bubbles. Their edges are smooth, and their interiors relatively uniform, as if filled in a single episode or in a few episodes by energy launched from the center. Magnetic fields likely helped confine and shape those lobes, and weak shocks along their rims indicate expansion into the halo. If the lobes are indeed linked to a past outburst, then the echoes in the clouds are the inner traces of the same season, small and crisp, where the gas is dense, broad and gentle, where the halo is thin. In this way, the sky around the center becomes a palimpsest on which multiple instruments can read different handwriting for the same event. With each new year of data, the echo maps refine. Some regions that were bright have faded, and new peaks have appeared along nearby ridges like beads passing along a string. This drift is a blessing for interpretation and a challenge for patience, because the total pattern unfolds on human timescales. The task now is to continue the slow movie, to combine high-energy light with radio and millimeter maps that show the detailed shapes of the clouds, and to improve distance estimates so that the inversion from patterns on the sky to timings in the past can sharpen. The central lesson already stands. The monster at the heart of the Milky Way is not fixed in any single mood. It cycles through quieter spells and active spells, and when it is active it reaches far enough to change the ionization and chemistry of clouds hundreds of light years away. The present hush is therefore not a guarantee of future calm. Among the streams at the inner edge, parcels of gas continue to form and break, and any one of them might one day push through into the region where efficiency improves and light pours out. When that happens, the lobes may fatten, the ion line echoes may begin their next crawl, and future astronomers may read our era in the delayed glow written across the clouds we monitor today. The quiet now feels less like an ending, and more like a pause between pages in a longer story whose lines are traced in light that travels not only through distance but through time. In galaxies where the central engine feeds greedily, jets lance outward in narrow beams that carve their presence into radio maps and X-ray images with a clarity no one can miss, but the Milky Way hides its answer, offering hints and fragments that invite the idea of a jet without granting it outright. Around the core, fine structures appear that look as if something once pushed straight through the clutter. On scales of a few dozen light-years, radio maps reveal filaments that stand nearly vertical to the galactic plane, as if taut wires tie the inner region to altitudes above and below. On larger scales, pillars of high-energy light rise like pale chimneys, in X-rays connecting the center to the soft edges of the giant gamma-ray lobes that bloom in both directions. Polarized radio emission traces ordered fields along parts of these paths, and the alignment suggests that a coherent source once drove particles upward and downward along channels that are not fully erased by time, Yet the core today is quiet and no bright narrow jet shoots directly from the compact source into open space. The puzzle is how to reconcile the family resemblance to jet-drawn galaxies with the present hush. One option is that the engine does produce outflows, but they are weak, intermittent, or quickly disrupted by the crowded medium, so they leave only the tidy remains at a distance where the clutter thins. Close to the compact source, the flow is hot dilute and threaded by strong magnetic fields. Magnetic stresses can tap rotational energy from the inner plasma and possibly from the black hole itself, if the field grips the spinning space-time, launching a pair of oppositely directed outflows, even when the inflow rate is small. In a starved state, such outflows would be light, carrying more magnetic energy and a few fast particles than heavy loads of gas. They might flare into focus only during the briefest of feeding spells, when a clump crosses into the tight orbits and twists the field into a sudden nozzle. The event horizon, telescope's ring-like image, provides a subtle clue consistent with a preferred orientation. The brightness is not uniform around the ring. One side glows more strongly, and that lopsidedness can be explained partly by motion in the inner flow that beams light in the direction of travel, but it also opens the possibility that the inner field is threaded along a particular axis. If so, the faint base of a jet might be there, too blurred by scattering and too modest in power to stand high above the background, yet strong enough to order the plasma and polarize the light on timescales of minutes during flares. Near-infrared flares sometimes show a smooth rotation of the polarization angle, as if a compact knot orbits while its magnetic vector turns, and in a few of those events the preferred swing hints at a stable axis in the inner geometry. The radio core itself shows rapid variability on hourly scales and changes in polarization that imply an evolving but structured field, and in some epochs a slight extension appears in very long baseline images that could be read as the ghost of a compact outflow. The difficulty is that local winds from massive stars' supernova shocks and ram pressure in the circumnuclear region can mimic, mask, or shred any gentle jet bending it before it clears the inner 2 or 3 light years. The evidence may therefore survive better at larger heights where the medium is thinner. There the gamma-ray lobes rise for thousands of light-years, with edges that are smooth and with interiors that are surprisingly uniform, the sort of shapes that long-standing gently pressured outflows would inflate. Radio observations find a microwave-scale glow that fills the same general volume, a haze of relativistic electrons that could have been lifted and confined by magnetic walls. Between the very center and these giant balloons, elongated X-ray structures, sometimes called chimneys, run roughly perpendicular to the plane, as if the energy had flowed along corridors to feed the lobes. If these features are indeed part of a single story, then the Milky Way once ran a jet or a strong wind in a mild, perhaps sputtering mode long enough to pump energy into the halo, but not in a way that left bright, narrow radio beams near the source. Another piece of circumstantial support comes from catalogues of small comet-shaped sources in the central few light-years where stars drive bow shocks with their winds. A subset of these bows align preferentially their tails, pointing away from a similar axis, as if a large-scale breeze pushes them in a common direction. Alignment could also arise from local flows along the ring or streams, but the pattern keeps the jet hypothesis in play by showing that the center has more than one set of ordered motions. On yet larger scales, very old radio spurs and arcs flank the galactic plane near the center in ways that might record shocks from past outbursts that were less tightly focused than a textbook jet, yet more organized than random star-forming turbulence. The notion of a silent jet also makes sense in the energy ledger of a starved black hole. When the accretion flow is thin and hot, more energy can leave mechanically or magnetically than radiatively. The flow becomes thrifty with light and generous with momentum. Winds rise from the disk and carry away mass and spin. If a significant bundle of magnetic flux is dragged inward, a magnetically arrested configuration can form that resists further inflow and redirects energy into vertical channels. Such channels could be intermittent, turning on when flux builds up, turning off when reconnection relieves the tension. They could also precess if the inner disk is tilted relative to the black hole's spin axis, smearing any small-scale jet into a broader cone that, seen through dust and confusion, would be hard to distinguish from a wind. Precession would leave faint helical imprints in polarization, and in the placement of compact knots, patterns that present instruments only barely touch. The counter-arguments are honest and important. Direct imaging of a narrow, bright jet base has not been achieved. The compact source's radio spectrum and size evolution with wavelength can be modeled without invoking a collimated outflow, relying instead on a stratified magnetized inflow, whose emission region expands with wavelength because of optical depth and scattering. The straight radio filaments that rise from the central hundreds of light years could be produced by magnetic shear and local particle acceleration unrelated to the compact source, and the gamma-ray lobes might have been inflated not by a jet but by a broad nuclear wind or by star formation feedback integrated over time. Even the chimneys could be the combined effect of many supernovae venting along the least resistant paths. The balance of evidence, therefore, does not force a jet. It leaves a persistent invitation. The most economical synthesis is that the central engine can drive outflows across a spectrum from wide winds to brief narrow jets, with the exact form depending on the current balance among spin magnetic flux and fuel. In rich seasons, a better focused jet might appear. In lean seasons, a broad faint wind may dominate, and in most seasons the record is written more clearly at altitudes where the medium is light. The Milky Way would thus be a gentle cousin of the famous jet hosts, operating in a low-power mode that still sculpts the halo on long timescales. In this view, silence is not the absence of a jet, but the difference between a shout and a whisper. The galaxy's heart may whisper most of the time, and the sky carries those whispers far in lobes that outlast the voices that made them. The next advances will come not from a single dramatic snapshot, but from years of coordinated timing and polarization across wavelengths, catching the small repeatable turns of the inner field and the corresponding tremors along the larger corridors. Until then, the possibility of a jet remains a graceful thread tying the quiet ring to the tall bubbles, a line drawn faintly but with a steady hand through the crowded center of the Milky Way. To see the outline of a place where light itself cannot escape astronomers, build a telescope the size of Earth, not by pouring a single mirror, but by lacing radio dishes across continents into one instrument that listens in concert. This is the Event Horizon Telescope, a worldwide array that links stations by shared time kept with atomic clocks, and later combines their signals so that the separations between dishes act like a vast lens. In ordinary galaxies, the central engines flicker too quickly and sit behind screens of turbulent plasma that blur the finest detail. In the Milky Way, both challenges are present. The compact source at the heart of the galaxy varies on timescales of minutes, and the radio waves that leave the inner flow must cross an interstellar fog that scatters them, spreading the image the way frosted glass spreads a candle flame. Yet both hurdles can be crossed by observing at short millimeter wavelengths where the scattering is weaker and the inner flow is brighter, and by letting networks of computers sift many brief snapshots for coherent structure. A ring-like image emerges whose size and lopsided brightness speak to gravity strong enough to bend light into arcs around the void. The effort draws on years of rehearsal at longer wavelengths, and on earlier work with another galaxy, whose central engine is larger and steadier. That distant cousin in the Virgo cluster presented a thick orange ring, whose size and orientation matched the expectations for a supermassive black hole seen nearly face-on. The ring around the Milky Way's core is harder to hold still. It brightens and dims while the array is looking, and pieces of the ring seem to shift because hot knots orbit quickly close to the point of no return. The solution is statistical. Rather than rely on a single frozen picture, the teams reconstruct an average ring that stands above the motion, testing the fidelity of that average against synthetic data made from computer models that include magnetized turbulence and rapid rotation. When the moving parts are accounted for, a stable size appears. The ring measures roughly 50 microarc seconds across a tiny angle on the sky that corresponds to a few tens of times the radius where light would circle in the last stable path. That scale agrees with the mass inferred from stellar orbits, an independent check that binds dynamics and imaging in a single frame. The lopsided brightness carries its own meaning. In a hot magnetized flow, plasma moves at a fair fraction of the speed of light as it orbits near the edge, and the glow from the side that approaches is beamed toward the viewer, while the opposite side is dimmed. This natural asymmetry produces a crescent bright on one edge and fainter on the other, and it requires no extra lamp or hidden jet to appear. The same Doppler beaming also pushes the polarization into patterns that depend on field geometry. So when the array measures the ring in polarized light, the data test whether the inner flow is dominated by orderly threads of magnetism or tangled fields that blur into a simple fog. The first polarization maps of the ring show swirls and patches that favor strong-ordered fields near the innermost orbits, a result that ties the imaging to the flare physics and to the idea of a magnetically arrested state. The choice of wavelength is a compromise between scattering and sensitivity. At shorter wavelengths, the scattering fades, but the atmosphere becomes a fierce partner, and only the highest, driest sites can join the array. Calibration must be brutal and honest, separating instrumental quirks from sky signals, and the final synthesis demands cross-checks that confirm that the same ring appears when the data are carved in different ways. The closure quantities measured by the array help in this because they are built to cancel out certain errors and leave only the true sky structure behind. When these closure phases and amplitudes are compared with models, the ring solution persists, and the size remains fixed within the uncertainty. The time variability still poses a challenge, because the core changes while the array traces its long baselines, different parts of the Earth-sized lens sample, slightly different rings. Catching the average requires multiple runs spread across days with weather windows at every site. It also requires careful modelling of interstellar scattering, whose small ripples change the apparent shape of the ring on timescales of hours. Descattering algorithms, informed by years of monitoring of compact sources along the same line of sight, help undo this blurring, and the remaining structure is consistent across independent approaches. The image that results does not show a surface. The dark center is not a disk or a crust. It is the shadow cast by the photon orbit, and the event horizon together a deficit of light, where paths are bent inward and lost. Around that deficit, photons from the inner flow are lensed into a thick circle, whose diameter is set primarily by mass and only weakly by spin or other details. This insensitivity is a virtue because it means the ring is a clean ruler for mass. The measured diameter agrees with the few million solar masses that the fast stars demand, and so two very different experiments converge. One weighs by motion, the other weighs by light's path. Where they meet, the case for a supermassive black hole is no longer a chain of inference, but a linked pair of direct probes. The comparison to the distant cousin in Virgo adds context. That galaxy's black hole is more massive by orders of magnitude and feeds more steadily, so its ring is larger on the sky and easier to freeze in a single exposure. The Milky Way's engine is smaller and more mercurial, so the image carries more smear from motion. Yet the physics is the same. In both cases, the ring's size supports the mass. The crescent's asymmetry supports fast orbital motion near the edge, and the polarization supports magnetic order in the inner flow. The differences between the two images become a study in feeding regime rather than a contradiction. The Milky Way shows what a starved engine looks like at the brink of the horizon. The work is not finished. It has only begun. Future campaigns aim for shorter wavelengths where scattering is weaker and the ring can be traced with finer detail. They also aim for more stations, especially in the southern hemisphere, to fill gaps in the vast lens and to let the array watch the ring's changes unfold with better temporal coverage. Movies of the inner flow are a goal-within-reach movies in which hotspots circle, fade, and are reborn, and in which the bright crescent nods as the balance between inflow and outflow shifts. Polarization movies would show the field lines turning stretching and reconnecting. If a faint jet base truly exists, repeated imaging might pull its footprint out of the noise. Even without that discovery, the ring will remain a daily test of models in which gravity, rotation, and magnetism compete and cooperate. The quiet wonder of the image lies in how little spectacle it needs to persuade. There is no explosion, no shock wave, no fireworks. There is a ring whose scale is fixed by gravity alone, and whose shape is bent by the speed of orbiting plasma. There is a dark heart that is not a surface but a simple absence that no light can fill. There is a match between mass by motion and mass by shadow that leaves little room for alternatives. The Milky Way's centre is not an idea drawn from distant quasars and transplanted by analogy. It is a place whose edge has been traced by instruments anchored on Earth and linked by time. The story that follows turns from geometry to ingredients, from the outline of the horizon to the strange survival of molecules and dust in the harsh field nearby, because even in the roar and the hush of gravity, chemistry finds corners where it can persist, and those corners carry new questions about how life can cling to order in a furnace built to unmake it. Close to the heart of the galaxy, where radiation is harsh and shocks are common, chemistry persists in stubborn, surprising ways. Clouds in the central molecular zone carry dense pockets that shelter molecules which would seem too fragile for such a place. Radio and millimeter observations pick out lines from hydrogen cyanide, formyl ions, silicon monoxide, ammonia, methanol, and even more complex organics with several atoms tangled into shapes that would be at home in calmer nurseries far from the core. Some of these signals rise from famous clouds with heavy names, sprawling reservoirs of gas that lie within a few hundred light-years of the centre. Others come from smaller knots and streamers that thread the circumnuclear ring and drift inward like braided smoke. Along many of these lines, mass emissions from water and methanol flare like beacons, announcing pockets of dense gas that are warm, shocked and actively changing. The survival of such molecules is not easy to explain if one imagines a steady bath of hard ultraviolet light, and X-rays tearing bonds and a sea of fast cosmic rays ionizing everything in their path. Bonds do break in the open, and in some places the chemical mix is indeed reduced to simple ions and atoms. Yet the region is not an open plain. It is a carved landscape of shells, folds and filaments, where dust piles up into thick layers, and where the interiors of clumps become small worlds with their own weather. In those interiors, ultraviolet light is blunted by grains of silicate, and carbon X-rays are softened or scattered, and the rate at which cosmic rays penetrate depends on the density and the geometry. Where the shielding is deep enough, molecules can form on dust surfaces and then desorb into the gas when a passing shock warms the grains, or when a burst of infrared light shakes them. Laboratory studies and computer models both suggest that icy mantles on dust grains act as workshops where simple atoms meet stick and combine in steps that would be too slow in thin gas. The central zone supplies those mantles again and again. Dust grows ices in the dark inner folds, then loses them in the next shock, then grows them again downstream. Each cycle writes a new chemical sentence on a surface the width of a bacterium. Shocks are not only destructive, they are also creative. When a clump collides with a fast wind, or when a spiral arm inside the ring meets a counterflow, a front of compression ripples through the gas. Temperatures rise to hundreds of degrees. Kelvin dense layers briefly form and the dust sputters, releasing atoms and simple molecules into the flow. Silicon is freed from grain cores and quickly oxidizes, leaving silicon monoxide to mark the track of collisions. Methanol formed on dust sublimates into the gas, and sometimes acts as the amplifier for maser lines that reveal the geometry of shocks with map-like clarity. Hydrogen cyanide and formyl ions are boosted in regions where ionization is high, and where the balance between dissociation and formation favors a rich but transient mixture. After the shock passes, the gas cools, the chemistry relaxes, and some complexity is rebuilt on grains ready for the next passage. The field of radiation from the central engine and from the crowd of hot young stars adds another layer. In the open skins of clouds nearest the center, hard light strips electrons and builds surfaces that glow in fine structure lines. These photon-dominated layers act as shells around cooler cores, and the thickness of a shell depends on the strength of the light and the local density. Observations of carbon monoxide, neutral atomic carbon and ionized carbon combined with lines from nitrogen and oxygen let astronomers estimate how deep those shells run. The answers vary across the region, but they share a theme even in the presence of harsh light. High density and rapid turnover carve out safe rooms where complex molecules can exist for long enough to be seen. The same is true for X-rays. They penetrate more deeply than ultraviolet light, but their effects are patchy. Strongest near channels that lead back toward the core and weaker behind thick ridges. In some clouds, the ionization level inferred from certain molecules is so high that only a strong past burst can explain it, an echo of the recent activity traced by ion line reflections. Here chemistry becomes a chronometer. Ratios of molecules with different sensitivities to ionization record the time since the last hard wave of light passed. In this way, the gas not only survives the center, it remembers it. Winds from massive stars and the shells left by their deaths complicate and enrich the picture. Bow shocks around individual stars scoop and compress gas into arcs that face away from the center. Where many arcs overlap pockets of compression seed short, lived clumps inside which the chemistry can leap forward. Supernova remnants push on clouds and break them into globules that collapse or disperse depending on the balance between pressure and gravity. In a few places, dense hot cores appear regions that may be forming stars within the central zone despite the strong tidal field. Whether those seeds flourish or are torn apart before they can fully ignite remains an open question, but their chemistry resembles that of star-forming cores elsewhere, with sulfur-bearing species, nitrogen-rich molecules, and complex organics appearing together in distinctive bundles. This circumnuclear ring serves as both corridor and filter. Gas that arrives along the bar of the galaxy carries the chemical memory of the wider disk. when it meets the pressures and fields of the inner ring, that memory is partially erased and rewritten. Molecules that were abundant in calm cloud interiors may be destroyed or driven onto grains, while molecules that favour shock and high ionization flourish. By surveying many positions around the ring, observers see this script vary with position. Near the points where inward streams strike the rim, shocks are common and silicon monoxide is strong. Downstream from those points where gas has cooled, more complex species rise. Where the ring's inner edge feeds spiral arms toward the core, ionized layers thicken and traces of high-energy processing brighten. The pattern is not static. Flares from the core, even if brief, wash across parts of the ring and alter ionization and temperature in ways that leave chemical afterimages for years. In this sense, chemistry is a slow camera that records the passing moods of the center. The most evocative fact is that large organic molecules can be found at all in such a place. Their presence does not claim life or direct precursors of life, yet it shows that carbon chemistry is resilient in environments far harsher than the quiet backwaters of the spiral arms. It shows that dust grains are more than passive passengers. They are active sites where order arises from collision and sticking, and where that order can be returned to the gas in bursts. It shows that the galaxy's heart, while a furnace in many respects, is also a workshop with many benches, some noisy and hot, some quiet and shaded. The questions that follow are practical and deep. How does the rate of cosmic ray ionization vary from cloud to cloud, and how tightly is it tied to the recent history of outbursts? How much of the observed complexity is rebuilt after each shock, and how much is carried inward intact in sheltered cores? Do the inner spirals feed the black hole with gas that has passed through many chemical cycles, and does that history matter for the way the inner flow radiates? As telescopes sharpen, and as surveys expand to cover more species with finer resolution, the answers will emerge molecule by molecule. For now, the lesson stands quietly, even under a sky where gravity bends light and stars race like sparks around an anvil. Chemistry holds on. The molecules do not cancel the monster. They make its neighborhood legible, and they invite the thought that order can rise and fall many times within a field of forces that seems at first designed only to unmake. The presence of a supermassive black hole at the center of the Milky Way invites a question that looks backward through cosmic time. How did a well of a few million solar masses come to sit so quietly at the focus of a spiral galaxy whose arms still form stars? The answer is not a single story, but a family of paths that could converge on the same result, each leaving subtle fingerprints that astronomers now seek in the motions of stars, in the chemistry of the central clouds, and in the faint fossils of past outbursts. The oldest possibility begins close to the dawn of structure, when the first dark matter halos gather gas and cool it. In that early era, under conditions of low metal content and strong ultraviolet backgrounds, a massive cloud can avoid fragmenting into many small stars and instead collapse almost in one piece into a single enormous object. Such a direct collapse could seed a black hole with a mass of tens of thousands to hundreds of thousands of suns in one step. If such a seed fell into the growing Milky Way protobulge and sank to the center, through dynamical friction, it would already be a heavy nucleus that later accretion could build upon. In this path, the present modest mass would be the end of a gentle growth rather than the sum of many small beginnings. The second path invokes many smaller seeds from the deaths of the first generation of massive stars. Those stars born when cooling was poor and fragmentation limited were likely heavier on average than stars born later. Many would have ended as black holes of a few tens of solar masses. In a crowded protobulge, some of these remnants would sink toward the center, form dense clusters and merge over time. Their inflow would be helped by the swelling of the central potential as gas rained in along early filaments. In this picture, the central object grows through a series of meals and marriages, its mass climbing by factors of a few, with each important merger, while long quiet spells let it settle. If such a history dominated, traces might remain in the spin. Repeated random mergers tend to scramble spin directions and leave a modest net rotation, while steady prolonged feeding from a disk tends to spin a black hole rapidly in a stable direction. Measuring the spin of the central mass, a difficult task that demands exquisite timing of very close orbits or detailed fitting of polarized ring images, could therefore tilt the balance between histories. A third contributor is the galaxy itself, which is not a static stage but a living system that has likely swallowed smaller companions. Each dwarf galaxy may carry its own intermediate mass black hole at its core, and when the dwarf is torn apart by tides, the core remnant can sink to the Milky Way's center over many orbits and merge with the resident whole. These minor mergers would add both mass and potential kicks. Some kicks could tilt the spin, others could drive short episodes of activity as new gas is stirred, and the pattern of star orbits in the inner few light years might record the past disturbances as slight asymmetries or as families of stars with shared inclinations. Searches for faint stellar streams and for compact star clusters on eccentric paths near the center are in part hunts for these ancient crumbs. Feeding history also matters because mass that does not arrive cannot be added. The Milky Way has not been a quasar in living memory, and the echoes in iron lines suggest that centuries ago the center was louder, but not deafening. This relative quiet implies that for most of recent cosmic time the inward delivery of gas has been limited by angular momentum barriers, and by winds that remove material before it can cross the last steps inward. If the past were rich in long thin disks feeding the whole at high rates, the present mass might be much larger. The modest mass could therefore be the result of a gated supply set by the structure of the bar and the circumnuclear ring, and by feedback from the core itself whenever it rose from hunger to feast. This self-regulation would have kept the central object in the millions rather than tens of millions of solar masses, and it would have preserved the spiral disk from the disruptive violence of a long-lived quasar phase. A different line of clues comes from the young massive stars within a few light years. Their ages and arrangements point to one or more bursts of star formation close to the center within the last few million years. These bursts require dense gas near the core, which in turn requires deliveries that overcame tidal shear for a time. If those same deliveries sent some fraction of their mass inward past the ring, the black hole would have enjoyed a brief rise in feeding as well. The coordination of star formation rings and black hole growth is a broader theme seen across galaxies, and in the Milky Way it hints that the central object may grow in pulses, linked to the same inflow events that build short-lived stellar disks. How far back these cycles run is unknown, but the large gamma ray lobes above and below the plane suggest that at least once in the last several million years the center launched enough energy to inflate structures that now dwarf the entire bulge. The nature of that launch remains debated, yet whether it was a broad wind or a focused jet, it implies that the engine can, under the right conditions, couple to the halo with vigor. If the black hole grew through such phases, then its current quiet is not a permanent trait, but one side of a long rhythm. Another speculative path folds in dark matter in a more direct way. Some models imagine a dense clump of dark matter forming a steep cusp at the center and feeding the growth of the black hole both by adding to the gravitational pull and by serving as a reservoir that focuses baryons. Others suggest that annihilating or decaying dark matter could contribute to the heating and ionization budget in the central region, subtly changing the chemistry and the pressure balances that regulate inflow. These ideas remain on the edge of evidence, and so far the cleanest measurements of mass and dynamics do not require such extra ingredients, but the center remains the place where such ingredients would show earliest, if they play a role at all. The question of origin also touches the spin and tilt of the inner flow today. If the angular momentum of gas arriving from the bar and ring has changed direction over time, the inner disk may be misaligned with the black hole spin. When that happens, general relativistic torques can twist and align the inner disk, dissipating energy, and possibly creating warps that in turn influence how efficiently gas moves inward. A history of changing inflow directions could therefore leave the present engine in a mildly warped, magnetically arrested state that feeds in sputters just as observed. Capturing that past in a single number is impossible, but continued attempts to measure spin and to map the polarization of the ring at shorter wavelengths will turn speculation into constraint. The modest mass compared to the largest black holes in giant ellipticals is in this sense a clue rather than a shortfall. The Milky Way is a barred spiral with a long history of orderly star formation and only occasional major mergers. It is a system that favours slow cooking over flash frying. A seed, whether large by direct collapse or small by stellar death, could have settled early, grown through a mixture of mergers and meals, and then entered a long era where the bar delivered gas in limited doses that built stars as often as they fed the core. The result is a central object heavy enough to hold the inner city together, light enough to have spared the disk a quasar storm, and active enough in brief seasons to inflate balloons in the halo and to write echoes in iron across nearby clouds. This balanced history is not a single neat narrative. It is a set of overlapping paths whose intersections lie in the data already in hand. Future measurements of the black hole's spin better maps of the younger stellar disks. Deeper searches for the remnants of swallowed companions and movies of the polarized ring will tighten the choices. Until then, origin remains a story told with careful humility, a seed planted early, a life of growth through patient accumulation, and a present in which the engine dozes between small meals, carrying the memory of a past that was sometimes louder, and a promise that quiet is not the same as stillness. The monster at the centre does not promise spectacle on demand, yet the ingredients for a louder season gather with slow patience, and the observers who have learned to read the inner weather prepare for the next shift. Streams from the circumnuclear ring continue to wind inward like narrow roads that end in fog. Massive stars still shed winds that collide and carve shells that drift toward the core. The bar of the galaxy continues to torque gas on scales of thousands of light years, and feed deliveries toward the inner few hundred. Any one of these channels can thicken, any one of the clumps within them can lose enough spin to cross from hovering orbit to inward slide, and when that happens the quiet state will respond not with a single firework, but with a season of faster breathing. The likely signatures are already known in outline. Near-infrared flares will grow brighter and more frequent. X-ray brightenings will rise not once but again and again, perhaps clustering over months, as fragments from a single delivery arrive in sequence. Millimeter light will show delayed humps as the energized plasma expands and cools. Polarization will swing sometimes smoothly, as compact knots orbit close to the edge, sometimes sharply, as magnetic reconnection tears through loops that have been wound too tightly by shear. The linked dishes of the planet-sized radio eye will catch a ring whose bright crescent nods and changes as the balance between inflow and any outflow shifts, and if a faint jet base exists at all, repeated imaging may pull its footprint out of the noise with the patience of a tide sculpting ashore. The scale of a future awakening need not be enormous to matter. A modest rise in the rate at which gas crosses the last few steps inward can lift the luminosity by orders of magnitude in high-energy bands without turning the galaxy into a quasar. Such a rise would puff the inner flow harden the spectrum and perhaps seed a brief narrow outflow that pierces the immediate clutter before fading in the thicker medium beyond. If a dense clump comparable to those spotted in the last decade finds the final ramp, the inner flow will be tested in a way models can confront cleanly. Does the system slip into a magnetically arrested state with clear signatures in polarized light, or does it remain a thin hot trickle with flares as its main expression? Do the near-infrared light curves show the gentle quasi-periodic wiggles that reveal orbiting hotspots near the innermost stable path, or do they smooth into longer humps that signal broader rearrangements? Each possibility stands as a branch on a tree that observers will climb with data rather than preference. The next generation of instruments make such climbing more secure. The extremely large telescope will watch the close stars with a precision that turns tens of micro-arc seconds into ordinary steps, allowing not only the steady relativistic periapse precession to stand out clearly, but also opening a path to the frame dragging twist that would betray the spin of the central mass. If that spin can be measured, its magnitude and tilt will tie the present engine to its past, distinguishing a life built by steady aligned feeding from one built by mergers and changes of direction. The James Webb Space Telescope, though blinded by the thickest dust at visible wavelengths, reads the warm infrared with clarity, and its stable platform above the atmosphere allows steady monitoring of the inner glow during long stretches that ground-based observatories cannot sustain without interruption. Combined campaigns that hand off from one facility to another will build light curves that cover hours, days and weeks without gaps a necessity if a season of heightened activity unfolds. The Event Horizon Telescope collaboration aims to grow into a denser network with more stations to fill the Earth-sized lens, and with shorter wavelengths to tame scattering further. Movies of the ring are not a metaphor but a goal, movies in which bright knots circle, fade, and are reborn, with the cadence of orbits measured in tens of minutes. Polarization movies will let field lines be seen in motion, turning a static map into a sequence that exposes reconnection and flow. If a faint jet base brightens, even briefly, repeated frames may reveal a small asymmetry that points along a stable axis, a signpost that other bands can follow through the clutter. On larger scales, monitors of the giant gamma-ray lobes will watch for slow changes along the rims, while X-ray maps will continue to track the chimneys that bridge the inner region to the halo. If a sustained rise in central power occurs, the chimneys may brighten in steps that climb outward, with the speed of a wave of energy, rather than the speed of sound in cold gas. Farther in, within a few hundred light years, clouds that once acted as pale mirrors for hard light may begin to glow again, with the narrow iron line that marks illumination by high-energy photons, and the moving patches of that glow will start a new crawl, whose pace will tell future readers when our era of activity truly began. The chemistry will answer too, with ratios of molecules that tilt toward higher ionization, and with fresh signatures of shocks where outflows ram the surrounding medium. Even the population of fast stars will join the conversation. If brief increases in the local radiation field alter the winds of their hot atmospheres and shift the shapes of their bow shocks, small changes that precise imaging can record as a census of pressure across the central parsec. The most profound change would come if a close star on a very tight orbit reveals a subtle precession out of its plane, the signature of frame dragging by a spinning hole. Such a detection would connect the destiny of the next flare to the history of the first seed, because spin holds the memory of growth, A rapidly spinning mass would suggest prolonged aligned feeding or a major early collapse. A modest spin, especially if the tilt is odd, would favour a history of mergers and changing inflow directions. Either answer would close one set of paths and open another, and the patterns of polarised light near the ring would be read with new eyes in light of that measurement. The monster will awaken again, but awaken in its own way. It will likely not produce a sudden single blast that transforms the night sky. It will more likely thicken its breath, producing clusters of flares that repeat slightly brighter, slightly longer, superposed on a slow rise that lasts months or years before fading. It may pump a gentle wind that stiffens the straight radio filaments and pushes on the inner edge of the ring. It may rarely focus a narrow outflow for a time that leaves a faint, tidy trace high above the clutter. Any of these would be enough to rewrite the present quiet into a new chapter. The task is prepared. Networks of telescopes set their clocks together. Software that can separate motion from structure grows more skilled. Catalogues of fast stars wait like rulers laid along the edge of space-time. Chemists of the sky tune to lines that carry memory. No law of nature promises that the next season will unfold while these tools are fresh, yet nothing prevents it either. The centre is a place of slow cycles and sharp surprises. It will feed again because gravity keeps its debts, and because the galaxy continues to deliver small payments. When that future arrives, observers will not be shocked by the glow. They will be ready to weigh it, time it, polarize it, image it, and fold it into the growing portrait of a black hole, whose quiet is an art of restraint rather than an absence of power. The last open question is the only honest ending. How will the next awakening differ from the last? The answer waits in streams already moving in knots, already forming in fields, already wound and in light, that will soon begin another journey from the middle of the Milky Way to the instruments that sit under Earth's sky and listen.